welcome you all again for the thermodynamic lecture series. So in the today's lecture we are going to discuss about a second law of thermodynamics. And so before entering into the second law of thermodynamics, so we need to know about three parameters. Okay, so that is the three terms we need to know about it. The first one is your heat reservoir or thermal energy reservoir, and second one is the source, and third one is the sink. Okay, so that is what is meant by a reservoir. A reservoir is a storage body. Okay, so reservoir which stores a type of energy or heat or anything. Okay, so reservoir means it can store anything. Then it can supply whenever we need it. It can supply an amount of heat or energy or any type of a system. Okay, but here we are going to study about a thermal energy reservoir, that is a heat reservoir. Okay, so that is the heat reservoir will stores certain quantity of heat. When a thermodynamic application needed, it will supply heat, or it can absorbs heat from a different types of body. Okay, that it is a storage device. Okay, so that the large body has heat enters or leaves are so very slow. So this process is also a quasi-static process, that heat reservoirs. Okay, and the second term is called source. The source is a higher type of heat reservoir, that is higher energy storage of your heat reservoir. That is a thermal energy reservoir from your high temperature. That is that heat can be transferred to heat engine. That is, it is of your higher temperature where the heat can be transferred from the reservoir to the heat engine. That type of reservoir is called as source. Then third one is your sink. So in the sink, where the heat is rejected and it is collected to one reservoir, is called as sink. Okay, so in that reservoir the temperature will be low as compared to your source. Okay, so these are all the three parameters we have to know before we entering into your second law of thermodynamics. So the second law of thermodynamics, again it is classified into two laws. That is, first one is your Kelvin Planck statement and second one is your Clausius statement. Okay, so in the Kelvin Planck states that it is impossible to construct an heat engine working on a cyclic process whose only purpose is to convert all heat energy is converted into your equal amount of work. That is, it is impossible to construct an heat engine. Whatever the heat supplied is given to the heat engine will not be converted into work done. There will be some losses of heat will be occur. So this is your Kelvin Planck statement. So Kelvin states that in a world it is impossible to construct an engine like this. Okay, so the entire amount of heat supplied cannot be converted into your work done. So it violates the first law. So based on the first law, you have found that there is the summation of work is not equal to summation of Q. That is the total work done. That is our total heat supplied cannot be converted into work done. But it can be converted with some amount of loss. That is, the some amount of heat can be rejected out of the heat engine with some amount of loss. So that is, this is the possible heat engine will prescribed by the Kelvin Planck. Okay. So second statement is your Clausius statement of the second law. So this Clausius statement said that the heat can flow from hot body to cold body. Okay, the heat can flow from hot body to cold body without any external aid. Okay, so but it cannot flow from cold body to hot body. Okay, so without giving any work. Okay, so without giving any work, the heat cannot transfer from cold body to hot body. So this is, here we are having one heat pump. We are supplying the work to transfer the heat from lower temperature reservoir to higher temperature reservoir. So this is possible system. Okay, so this statement is called the Clausius statement of your second law. That is, the heat cannot flow from lower temperature to higher temperature without any external aid. So we have to give some work or external aid to do the work. That is, we have to give some work to transfer the heat from lower temperature reservoir to higher temperature reservoir. So this is your Clausius statement. So Kelvin Planck states that, so it is impossible to construct an engine. That is, the total amount of heat supplied will be cannot be converted into work done. Clausius states that it is impossible to construct an heat engine to transfer the heat from lower temperature to higher temperature without any external aid. So with this we can move for a heat engine. What does I mean by heat engine? Okay, so as we all know, if you on to the heat engine, this thermal heat engine. So this heat engine will works when we supply heat. Okay, so this heat is supplied from the hot reservoir. So this reservoir will stores high amount of the temperature. From this high reservoir or hot reservoir, the temperature will be transferred, that is in forms of heat supplied, when a heat supplied is given to the heat engine. So this engine will gives out some work output, and so as per the Kelvin Planck statement, the total heat supplied cannot be converted into work. Here some loss of heat will be rejected. When a heat is rejected out of the system, then with the sign convention automatically it will be of negative. So net work done will be addition summation of your two heat supplied plus heat rejected, but this heat is rejected out of the system. As we know, it is a sign convention from the thermodynamics basic concepts. So you will put minus sign here. So work done of the net work done of the heat engine is heat supplied minus heat rejected. Okay, so in general the heat energy is a device which is used to convert the thermal energy into mechanical energy. Now we are going to derive an efficiency formula for this engine. Okay, so as we all know, the efficiency of any system will be output by input. Okay, so here you see that in an efficiency of your heat engine will be, what is the output in the system? Here the output of the heat engine is work done and input is your heat supplied. Okay, so output is work done and input is heat supplied. So you write the output of heat engine is work done and heat supplied. So work done can be written as heat supplied minus heat rejected divided by your heat supplied. Then you can divide the denominator by the each and every numerator. Then you will get efficiency equal to 1 minus QR by QS. Okay, then we can write this formula as heat is a form of, that is heat is proportional to it is a function of temperature. Okay, so heat is a function of temperature, that is as we all know, Q is equal to some mCp into T. So we can take it a function. Okay, so it is sum of the function or constant of a temperature. So I can take here efficiency equal to some constant into temperature here. Okay, that is QS, constant into temperature, that is this heat supplied is in from higher temperature reservoir, so we have to write TH, and this is QR is from lower temperature reservoir, so we have to write TL. So TL into constant, then this TH into constant, and TH into constant. So take it out all the constant outside, so you can cancel. Then your efficiency becomes TH minus TL divided by TH. Then your efficiency formula for your heat engine will be 1 minus TL by TH. Then second one is your heat pump. Here the heat pump is a device which is used to heat any system with lower temperature to higher temperature. Okay, for that we are giving some work. Okay, so we are giving some work. Here we are giving work is heat rejected to the heat pump as considered as heat rejected from the cold reservoir, and we are supplying some heat to that body to heat the system. Okay, so here the work done is QS minus QR as applicable for your heat engine, but we are giving work done here. In case of heat engine we are taking out of work, but in case of heat pump we are giving some work done. So here again output by input is your coefficient of performance in your heat pump. So what is your output here? The output is your heat supplied and your input is your work done. Okay, so output is your heat supplied, so QS divided by W. So QS can be written as QS minus QR. Again we know QS, that is Q is a function of temperature, so we can write QS is a hot reservoir temperature, so we can write COP of heat pump as TH divided by TH minus TL. The next one is a refrigerator. So refrigerator is a device which is used to remove heat from a cold system. Okay, so which is used to remove heat from a cold system. So consider this as a cold space. Okay, so from this space, that is refrigerated space, from this space we are removing heat. Okay, so this is your output and we are sending back to the atmosphere. Like this you have to assume. For that we are giving some work to the refrigerator. Okay, then your COP of your refrigerator will be output. What is the output of the refrigerator here? Here the refrigerated space output is, this is your output, how much amount of heat is extracted, this is your output. So QR divided by W, this is your work input we are giving. So coefficient of performance of refrigerator will be QR by W, then W is QS minus QR. Again we know that Q is a function of temperature, so we can write the coefficient of performance of refrigerator as TL divided by TH minus TL. Okay, so with this three basic terms. We can also discuss for a perpetual motion machine of the first kind. Okay, so what the perpetual machine of the first kind says, a machine which violates the first law of thermodynamics. Okay, so that is, such a machine creates its own energy from nothing and does not exist. The first law of says that one type of energy can be converted into another type of energy. Without any type of energy by its own, no energy cannot be produced. Okay, so that law is called as perpetual motion of the machine of the first kind. Okay, so here the perpetual motion machine of the second kind says that an imaginary machine which could continuously absorbs heat from a single thermal reservoir and converts this into completely work. The efficiency of the such machine would be 100%. Okay, so said that this and any engine will absorbs heat and it will produces work done as 100%. So it is also not possible. Then we move on to a Carnot theorem. A Carnot theorem or Carnot cycle says that any heat engine which operates between a two constant temperature, then it will becomes a more efficient reversible heat engine. Okay, then it will produces a maximum efficiency. Then we have some of the corollaries of Carnot theorem, that is, in all reversible engine operating between two given thermal reservoirs fixed with temperatures having same efficiency. And second one is, the efficiency of any reversible heat engine operating between two reservoirs is independent of the working fluid. Okay, so it does not depends on any working fluid of the system, but we have to depend only on the temperature of the reservoirs, not about the working fluid in the system. Okay. So in the Carnot cycle, we are having four processes, that is the two isothermal process and two isentropic process, and also we are having two compression process and two expansion process, that is the process 1 to 2 is named as isothermal expansion, and process 2 to is nothing but your isentropic expansion, and process 3 to 4 is nothing but your isothermal compression, and process 4 to is of your isentropic compression. So as we all know that when during the isothermal compression the temperature will get constant, temperature will be constant, and during your isentropic expansion the entropy is constant here. Okay, so isentropic expansion, that entropy is constant here, and during your isothermal compression again the temperature T3 is equal to T4, and again during compression, that is the process of compression is of about isentropic process or reversible adiabatic process. The process S1 is equal to, so process 1 to 2 is your isothermal expansion process. So here the pressure will get reduced with the increase in volume. So during expansion process the pressure will get reduced, that is V1 to V2, that is the pressure will get increased, so pressure will get reduced by increase in volume. Okay, with increase of volume V1 to V2, with reduction of pressure will happen in your isothermal expansion process. So for that I am applying your first law of thermodynamics in the process 1 to 2, then I can write it off Q is equal to W plus delta U. Okay, so here in this process the change in internal energy is 0. Okay, so delta U is equal to mCV into delta T. Here the change in temperature is 0 because T1 is equal to T2, so we can write T2 minus T1, that is T2 minus T2 either or T1 minus T1. So internal change in internal energy delta U is 0 for your isothermal process, so this delta U of U will be 0. Then we can write Q1 to 2 is equal to W of 1 to 2. Then your second process 2 to 3 is your isentropic expansion. So this is isentropic expansion or reversible adiabatic process. So in this process the entropy is constant. So we can write S2 is equal to S3. Since S2 is equal to S3, so there is no area under this curve. Okay, so apply your heat transfer. So apply your first law of thermodynamics here for the process 2 to 3. Then your formula will be Q of 2 to 3, which is equal to W plus del U. Okay, so here that is the heat transfer is 0 in this process, so we can write delta U plus work done of 2 to 3. So process 3 to 4 is again an isothermal compression process. So in this compression process we are having the temperature will be equal, T3 is equal to T4. During compression the heat will be rejected here. Okay, so since it is an isothermal process, so there is no change in internal energy delta U. Then you apply the first law of thermodynamics to the process 3 to 4, then becomes Q of 3 to 4, which is equal to delta U of 3 to 4 plus work done of 3 to 4. Okay, why I am putting minus n here? Okay, so that is here the heat is rejected out of the system. Okay, when a heat is during compression, the heat is rejected out of the system, so you have to put one minus in here. And also we are giving work to do the compression process. Okay, so here we are giving work, so it is also negative. So here heat is also negative and work is also negative in the compression process, in an isothermal compression process 3 to 4. Then process 4 to 1 is your isentropic compression process. So since it is an isentropic compression process, the entropy is constant. Again here there is no heat transfer here. Under the area of this 4 to 1 curve, there is no area here. So you apply the first law of thermodynamics to 4 to 1. So Q of 4 to 1 will be delta U of 4 to 1 plus work done of 4 to 1. Here again it is 0. So you keep the equation as it is. You see here this is an isentropic compression. Okay, so this is an isentropic compression. Okay, here heat is automatically 0 here. Okay, since it is an isentropic compression, we are giving some work to do the compression process. So again the work will be negative. Work done only will be negative in this case of 4 to 1 isentropic compression process. So with this we can apply the first law of thermodynamics, that is the net work transfer, which is equal to the net heat transfer here. That is the net heat transfer. So heat transfer in the process of 2 to 3 and 1 to 4. Okay, so process of 2 to 3 and 4 to 1. The heat transfer is 0 since it is an isentropic process, so leave those heat transfers, and Q1 to 2. So Q1 to 2 is heat supplied and Q3 to 4 is heat rejected out of the system from the compressor. So you put minus in here. Then you can add all the work done what we have find it out. Okay. Then this Q1 to 2 can be called as QS, heat supplied, and Q3 to 4 can be written as QR. This will be your total net work done. Okay. So the summation of work will be written as heat supplied minus heat rejected. As we all know, the efficiency will be your output by input. So here from the Carnot cycle, it is a work producing machine, so the efficiency will be output as work done. Okay, so the work done is work done divided by input is your heat supplied. So we can write efficiency is equal to work done divided by heat supplied. So work done is your heat supplied minus heat rejected divided by heat supplied. So heat is a function of temperature, so take it as the function as constant. Then it will be of higher temperature minus lower temperature divided by your higher temperature. That is, Qs can be written as T1, QR can be written as T3, and Qs can be written as T1 here. So the efficiency of the Carnot can also be written as 1 minus T3 by T1. Okay, so T3 by T1, that is 1 minus TL by TH. Then we move on to a reversed Carnot cycle. So in this reversed Carnot cycle, which consists of again 2 isothermal process and 2 isentropic process with 2 expansion and 2 compression process here. Okay, so here the cycle is reversed here. So in the process 1 to 2 is your isentropic expansion, and 2 to 3 is isothermal expansion, and 3 to 4 is your isentropic compression. Here the entropy is constant and heat transfer is 0. And 4 to 1 is your isothermal compression. In the isothermal compression, the temperature is constant. T1 is equal to T4. So process 1 to 2. So process 1 to 2 is your isentropic expansion process. Process 1 to 2 is your isentropic expansion process. In the isentropic expansion, the pressure will get reduced with increase in volume. So the volume will get increased from V1 to V2 with the reduction of pressure from P1 to P2. And process 2 to 3 is your isothermal expansion. So again the isothermal expansion is happened here. The temperature is constant here. So in isothermal expansion we say it is T2 is equal to T3 with increase in volume with reduction of pressure. It will get happened. Okay, so I am writing as a entropy formula here. Okay, so that entropy, as we all know, the entropy is equal to dq, change in heat transfer by your temperature T. So that is dq by T is equal to ds. Okay, so with this I can write q is equal to T into ds. Okay, so this q is equal to T into ds. Here the heat is extracted. So I can write QE. Okay, so during isothermal expansion the heat is extracted, QE or Q223, which can be written as T2, S3 minus S2. This T2 can also be written as T3 because since it is an isothermal process, as a result we can write QE is equal to T2 into ds. Then process 3 to 4 is our isentropic compression. So since it is an isentropic compression, the pressure will get increased from P3 to P4, and this volume is also simultaneously reduced from V3 to V4. And process 4 to 1 is your isothermal compression. So during your isothermal compression, the volume will get reduced and also the pressure will get increased. During isothermal compression, the pressure will get increased with keep on reducing its volume here. Here also I am going to apply the entropy relation. Qs, heat is supplied here, so heat supplied is equal to temperature into change in entropy. Here the temperature is T4, that is T4 is equal to T1 here. We can also be written as Qs is equal to T1 into S4 minus S1. So this can be written as ds. Okay, so change in entropy. So heat supplied is equal to T1 into ds. So with this, we can apply this reversed Carnot cycle for two different components. Okay, so two different devices. First one we are going to see about refrigerator, and second one we are going to see about heat pump. Okay, so how it is COP will be derived from the refrigerator and heat pump from the reversed Carnot cycle. Okay, so we know that the work done during the cycle. Okay, so the work done during the cycle will be heat supplied minus your heat extracted, or otherwise here we can just write that is minus W. Okay, so that is minus W is equal to QE. Heat is extracted from the refrigerator when it is given supplied to your atmosphere. That is minus W is equal to QE minus QS. That can be written as W is equal to QS minus QE. So QS is T1 into ds and QE is T2 into ds. So work done is T1 minus T2 into ds. So coefficient of performance of a refrigerator should be written as COP is equal to heat extracted from the refrigerated space divided by your work done. So heat extracted from the refrigerated space will be denoted as QE. Okay, so that is QE divided by QS minus QE, where QE is T2 into ds, where QS is T1 into ds. So in this term all the ds is common, so take it outside and cancel it out. Then your COP will be T2 divided by T1 minus T2. So that is T2 is your lower temperature reservoir, so it is TL. This is lower temperature TL, and T1 is your nothing but TH, higher temperature. So this COP of a refrigerator formula will be TL divided by TH minus TL. So work done during the cycle is again same here, but for the coefficient of performance of the heat pump, okay, it is a purpose of heat pump. Here is also we are giving some work to do. The higher temperature body into lower temperature body into high temperature body, we are supplying some amount of heat with providing some amount of work. So here the coefficient of performance will be heat supplied divided by your work done. So heat supplied is Qs divided by Qs minus QE. So Qs is again T1 into ds and QE is T2 into ds. So supply that value, then you will get take it out commonly ds outside, then you will get COP is equal to T1 divided by T1 minus T2. Then this T1 is your higher temperature. So this T1 is higher temperature and T2 is lower temperature. So T1 is TH divided by TH minus TL. So from this reversed Carnot cycle, so we can derive for refrigerator it is TL divided by TH minus TL, and it is for a heat pump it is TH divided by TH minus TL. So as a result, this Carnot cycle will be not in a practice, it is not possible. Why? Because in the Carnot cycle all the four processes are reversible, but in actual practice there is no process as a reversible process. Okay, and we are having the two compression and two expansion process. Okay, so you are considering during compression the piston will move fast, while doing your expansion process it moves a very fast process. In Carnot cycle they are said that during compression and expansion the piston will goes on the same speed. Okay, so but in the practical cases it is not possible, and also during moving parts is available, then it should be aware that it should be a friction will be available, but that friction is also be negligible in this Carnot cycle. So the Carnot cycle is not a practical cycle. Thank you.